Hello everyone, welcome to the Global Mapper Webcast for the month of October. My name is David McKittrick. I'm a Senior Application Specialist here at Blue Marble Geographics, and with me today is Katrina Schweikert.
Hello David, thanks everyone for joining us.
Good to have you here, Katrina, and one of our new faces here in the technical support team. Today we're going to be doing something a little different for our webcast. We usually answer questions. That's usually our approach. Those of you who have attended some of our live presentation have had the opportunity to ask us questions, and we will provide those answers. The tables are turned a little bit today because we're actually asking a question. As you can see on the screen in front of you, the question is, do I need the Global Mapper LiDAR module? We're going to be answering that question by way of showing you the features and functions that component of Global Mapper provides, as well as providing information on the LiDAR functionality that's available without the module. So we're hopefully going to provide you enough information that you will be well enough informed to answer that question.
So if you have questions about this presentation, you can reach out to us by email. That's geohelp@bluemarblegeo.com. We'll show that at the end of the presentation. And you can also check out the Global Mapper user forum if you want to talk with other users about some functionality.
That's correct. And again, those addresses, as Katrina mentioned, are going to be available on the final slide. So if you're looking at the recording, you can fast forward immediately, get those addresses, and you can be typing your questions as you watch this presentation. Our agenda for today is going to obviously ask the question, do I need the LiDAR module? And the first sub-question is going to be, what exactly is the LiDAR module? We're going to provide an overview, a high-level overview as to exactly what this component of Global Mapper is. We're going to spend a little bit of time at the start also introducing some of the new functionality that's been added specifically with the recent release of version 17 of Global Mapper. We'll provide information on what has been added to the LiDAR module. We will also have an opportunity to demonstrate some of those tools a little bit later in our presentation. I'm going to hand over to Katrina for this section, and we're going to take a look at Global Mapper without the module. To make it clear, you can actually use LiDAR data in Global Mapper without activating the module. It is fairly limited, but you certainly can work with your point cloud data, and we're going to go through the basic LiDAR processing functionality of the application. We are then going to activate the module. We'll actually have an opportunity to show you how that process works. And I'll begin the process of introducing the components of the LiDAR module by showing you the toolbar, the LiDAR toolbar that is activated when you apply the license to the LiDAR module. Most of our session today is going to be rolling our sleeves up and working with the components in the module itself. We have a number of scenarios that we're going to follow. The LiDAR module enables some advanced filtering tools. We're going to show you filtering things, point clouds by color. We're also going to introduce one of the brand new functions of Global Mapper, the LiDAR module in Global Mapper, and that's a noise filtering component. I've got some sample data to work through for that scenario. We're going to go through probably one of the more important components of the module, the ability to automatically reclassify points. Any of the unclassified data you're working with, you're not sure what it is, Global Mapper has a number of tools that will provide intelligence, provide more information about those points, and allow you to use them much more effectively, ground points, etc. So we'll get into a number of scenarios in regards to point classification. Related to that, we'll follow on and do some feature extraction work. Trees, buildings, new one is power lines, can all be extracted from a point cloud. I'm going to hand back over to Katrina for this one. We're going to take a look at one of the components of the module which allows you to create a surface based on either minimum or maximum values within a binned area. This gives you a DTM or a DSM, so it's a more advanced gridding process than would be available in the standard version. And we're going to wrap up today by readdressing the question, do you really need the module? We'll show you a side-by-side comparison of the functionality that each provides with the module, without the module, to allow you to make your decision. So the first section, the first of our bullets, the question is, what is the LiDAR module? I'm going to hand over to Katrina, and she's going to give us a high-level overview as to exactly what the module is.
Okay, so the LiDAR module is an optional add-on that you can add to Global Mapper. We started making it available in version 15. And so David mentioned that Global Mapper can read LiDAR data, but a lot of the power of processing the raw point cloud comes from this LiDAR module. There's a lot of advanced tools that apply intelligence to the point cloud data. So you can see at the top of the slide here, this is what the LiDAR module actually looks like. And we'll go in more detail into that as we continue. So you can request a trial license for this if you haven't purchased a license for this yet, and we'll talk about that in just a minute.
Yeah, we'll actually activate the module ourselves. Those of you who have actually used a previous version of the module may, based on the little screenshot that Katrina pointed out, notice there's actually a couple of new buttons, actually one new button up there. AN, we'll get to that one. So that the toolbar is the manifestation of the module, and we'll get into that, looking at that in the context of the software.
And so just to mention, this LiDAR module comes with a standard installation of Global Mapper. You just need the license to activate it. So you don't need to install anything new, you just need to obtain a license.
So yeah, everybody who downloads version 17 today they have the module, but it's activated with the license. And as with the standard license, you can request a trial. And we'll show you that dialog box in just a few minutes. So over to me. Next question, or next point here, is what's new in version 17? I figured we'd put this in at the start, so those of you who have been following the progression and the evolution of this component of Global Mapper will get you up to date as to what's just been added. And literally some of these functions have been added within the last couple of days. We've added an additional reclassification function, and this is very, very cool. I have some very interesting data we're going to work with a little bit later to identify and reclassify power lines. Now, before you get too excited about this, one of the caveats, one of the requirements is that your point cloud needs to be fairly dense. Some of the freely available point clouds that you can download, for instance, some of the data that's available through the USGS Earth Explorer site, they're probably not going to have the density of points that will allow you to do this effectively. But I've got a sample of some very high resolution or high point density point clouds, and it really does a fantastic job identifying power lines and then ultimately reclassifying those, leading into my second bullet, which is, as you can see, power line extraction, creating linear features from those. And again, we'll go through that scenario a little bit later. Third bullet, as you see, is a automatic point cloud noise removal. It's almost like a tongue twister. A tool for very simply removing those erroneous points from a point cloud, allowing it to be more providing you with a more effective and more precise model. It wasn't too difficult for me to find some sample data. Actually, the very first point cloud I rolled up, I found a lot of points that were obviously beyond the threshold of what would be normal. We'll take a look at that data today and remove those. So
all those birds.
May have been, actually, now that you mention. I didn't even think of that. We've probably got a few seagulls in there. We're right here close to the coast, so that's probably what it is. That doesn't account for the points that are under the ground, though. We'll address those as well. One of the things that's a little harder to demonstrate, but it is worth noting, is that we've really improved the processing speed in version 17 of the module. If you're doing any LiDAR processing, whether it's loading data, whether it's gridding data, or doing any of the processing of data, ground identification, significantly faster speeds. We actually did a little demonstration at our recent Blue Marble user conference where we measured the speed comparing version 16 to version 17. I believe it was about 15 to 20 times faster to process the data. So significantly faster processing of your point cloud data. And the final option here, we've got a number of new filtering options. I'm going to have an opportunity to show you a very powerful filtering dialog box that we've added to it. It has been there for a while, but we've added to it. I'm actually going to do a demonstration. We're going to do some filtering by color. But yeah, filtering options with the LiDAR module, very, very powerful component of the application. So as we promised at the start, we're going to give those of you who do not have the LiDAR module an opportunity to see what LiDAR processing functionality is available without the module. As I said, you can load a point cloud, you can do some very basic data processing, you can create a surface model, some very basic filtering as well, and Katrina's going to go through some of those basic functions.
Okay, so we've got Global Mapper version 17 open here, and we're going to take a look at some LiDAR data without the LiDAR module turned on. So I'm going to start by importing a sample data set that we have here of our nearby town here in Maine. So this is the first window that you're going to see when you import LiDAR data. And we really want to first start by looking at that raw point cloud so we can kind of get an idea of what exactly we have in this data set and if it has any classification of different types that we could use. So you can see right out of the box we could filter based on classification, but our point cloud might not have any of those classes yet. But if they do, we could use that, and we could also filter by the return type. There's also some filtering here we can do some basic noise filtering by deleting samples beyond the standard deviation. Some other things to load a smaller data set. LiDAR is usually pretty big to load some of those files that you might be working with. So we could start with a smaller file.
Yeah, and it's a good point you make there, Katrina. I'm very often asked when we introduce this dialog box, there is an automatic assumption that, I can perform these filters on my data before I import. I would usually recommend not. As Katrina mentioned, I would usually not recommend trying to filter at this stage without knowing more about your data. Obviously, if you've downloaded some data from an online source, you may not be sure what classifications are in there or what the quality of the data is. So it's a good idea to bring the data in, do some initial QA visualization, and then perform those filters. I should also mention that you can also go ahead and grid your data. Bypassing the point cloud rendering, generate a surface. Again, not typically recommended.
So let's take a look at what we have here for the raw point cloud. Okay, so the first thing that I can do is let's bring up the overlay control center. And we can look at what metadata this file has. So we can see the standard information here. We've got about 1 sample per square meter, a little more than that, in this data set. And particularly of interest here is going to be the statistics. So this is going to give you an idea of what exactly there is for classes and return types. And this particular data set right now just has unclassified data and ground data. It's about 50-50. So we're not really picking up yet on any of these features that you might be able to visually see, like, a lot of the sort of tree-looking things in here, some road-looking things. The data set is not aware of those things yet. And now let's take a little look at what exactly an individual point here has. So I'm using the identify tool, and let's just look. And right now I've got selected a point that is unclassified. Got a little bit of information there. I could also choose to look at the larger list of all of the points in this cloud using the search tool. So this is going to give me like my attribute table.
I would just caution again, this particular point cloud you may be able to see from the dialog box, the overlay control center just to the right of the screen. It's a relatively small point cloud. This is under 1 million points, which in the context of LiDAR is actually very small. If you have a much larger point cloud, and Global Mapper will support point clouds of billions of points, be aware that it's going to take a very long time to populate this tabular view. It's almost like bringing up an Excel spreadsheet.
Yeah, and you might actually get a warning that suggests that you use this on-screen features only function, to only look at a subset of what's loaded in the map frame back here. So that can help with the loading. So I've got return information, some other basic information here that I could use to understand the point cloud.
And of course you could build a query as well, just like any other vector data, if you want to.
Yep, so based on those attributes I could request certain records. And select them in my map window. So given what we've mentioned about how large point clouds can be, another cool feature that we can use here is to create a polygon that can inherit the metadata about the point cloud. So let's zoom back and see the full data here. So to do this, in my overlay control center, I would right-click on the layer and I'm going to go to bbox coverages. So that's going to create a bounding polygon. And let's just turn off my point cloud here for a minute so I can easily select this. And now, using the identify tool, so you might see this window. I do just want to look at this information within the information dialog of the application. So my polygon here now has the metadata that was the same from the point cloud. So this is a good way to share information about the point cloud.
So this is a very useful tool. If somebody sends you a point cloud, or if you inherit a point cloud, or download some data and you want a summary, what you've got as a result of this process is the bounding box, the geographic extent. And in this case, Katrina just shows a rectangular boundary. But if it was in a regular shape, it would create a boundary adhering to the bounds of the points. And it embeds the metadata. The metadata that Katrina had shown you a few minutes ago is now part of the attribute table for this single area feature. You can export this as a shapefile or in any of the supported vector formats. So it's a very nice little admin tool in a way for working with LiDAR data.
Okay, so turning back on our point cloud layer. So one of the real powerful tools in this application, of course, is the 3D viewer, and that's when we start to see some interesting things with our point cloud here.
This is where we get the oohs and ahs. Ooh, ah.
So here's our point cloud layer here, and let's see, we've got a little bit of an exaggeration here to help show some of that elevation. Could decrease that a little bit. But yeah, we can kind of check out our point cloud there.
And this works exactly the same way that a terrain layer works. Obviously, each point has a Z value or a Z value, so it will render as a virtual 3D model. And we're going to be coming back into this dialog box in some of our scenarios, looking at different versions of our point clouds, different point cloud data sets with different characteristics. But obviously the 3D viewer is a fundamental component of the application. It lends itself perfectly to the viewing of LiDAR data.
Okay, so let's go back to the map viewer here. And just as when we imported, we also have the option to filter the LiDAR points once we've loaded them. And the way to enable that is to go to Tools and the Configuration. And on the LiDAR tab here, I have the same filters based on return type or based on classification. So for example, we know that we've got some ground points here and we have some unclassified points. So if I just choose to remove the unclassified points, here's everything that has a ground classification in our data set. So that's a quick way to filter your data set, and that does not require the LiDAR module, but it's based on the classes that came with the original point cloud that you obtained. So the last thing that we can do is we can create that 3D terrain surface. I do that by going up to Analysis. I'm going to create an elevation grid from my 3D point cloud. And I do want to use the Gardner LAZ file. And I'm just going to stick with the defaults for this one. Let's turn off the points there. And you'll see from the hillshade, we've got a lot of texture in this detailed elevation.
Yeah, and in this example, it was obviously the raw point cloud. Katrina showed you the filtering process. He reversed that back. So this is essentially all points, whether they're classified or classified as ground or unclassified. So it may be a situation if you want to do a ground model, you just leave the ground points and then obviously generate an actual terrain surface. So there is one other point that I wanted to show. I just thought of it off the top of my head quite literally in regards to how you can interact with the point cloud data without the module, and that's simply point cloud management. We can select points very easily just using the digitizer. These are vector features, they're vector points. So using the digitizer in its native edit mode, you'll notice my cursor says edit right here. So it's waiting for something to be selected. I can simply drag a box to select the points that encompass the area that I've created. Or if I want more precision, I'm just going to right click. I'm going to go to my advanced selection options and I'm going to enable what's called poly select. This is not unique to LiDAR, but obviously it lends itself well to this application. Now I can simply draw a box, again, encompassing an area of interest, and right click to finish the selection. It will just select what's in that area. I could also draw an area or import a vector file and select all the points inside that area. So multiple ways of essentially selecting a subset of your points. And what I want to show you as well is Control, so you can't see what I'm doing, but Control C on my keyboard and Control V will allow me to take that subset and paste it into a new layer. And it's going to create a copy of the existing layer in terms of its name, but obviously then you get a smaller subset of your data if you need to just focus in on a particular geographic area or points that fall within a jurisdictional boundary. You have that boundary file. You can very easily crop down your point cloud using that. And again, that's a function not unique to LiDAR data and certainly not something that the module enables, but is a very useful LiDAR function.
Yeah, you could also do that based on existing vector data that you might have.
Absolutely, absolutely.
Apply some selections, yeah.
Obviously, there's a lot of functionality that's available even without the module. If you're just doing some basic LiDAR or point cloud processing, Global Mapper out of the box will give you a lot of functionality. Again, hopefully by the end of our presentation today, we'll entice you at least to try out the more advanced functionality that the LiDAR module provides. Now, to that end, we're going to transition into looking at the module itself. And you'll see the bullet on my screen here says the LiDAR toolbar. I'm going to talk a little bit about the functions of the LiDAR toolbar. I'm going to demonstrate some of the visualization tools for looking at a point cloud. In order to do that, one of the functions, inevitable functions we have to do is actually to activate the module. So I'm going to begin the process by showing you how you can activate the module. Now, if you have a current license, if you have purchased a module, it's simply a case of entering your order number. But if you don't, I'm going to show you that you can request a trial. So we're back looking at the same little sample point cloud that Katrina had used. And we're going to activate the module, and we're going to enable the toolbar and show you the functionality that brings. From the Help menu, you'll see our Module Extension License Manager. If I select that, it brings up a dialog box that shows me a couple of pre-embedded modules that are installed with the application, the LiDAR and OTF module. We're not concerned about OTF today, but the LiDAR module you can see is unchecked. And by the way, we're also not concerned about our extensions on the right side of this dialog box. The LiDAR module, if I check it, will immediately initiate the registration screen. And this should look very familiar to those of you who have used, who have registered your version of Global Mapper. I could simply enter an order number, as I mentioned before. I could connect to a network license. If your company or your organization has an active network license for which the LiDAR module has been applied, you can simply connect to that license server. I can select a license file, and this is actually what I'm going to do in a few minutes here. I'm going to actually connect to a local.lic file. The final option here is to request your trial. So if you have a currently active version of license for version 17, you can try this out for 2 weeks, and you can go through the scenarios or look at the tools that I'm about to show you today. For today, we're going to use the license file option. I'm going to select that button, and I'm going to click the Register Me button. And I'm going to browse, excuse me for 1 second while I delve into the innards of my directory structure here. And I'm going to choose a simple ASCII lidar17.lic file. I'll click open, and you will see immediately that the LiDAR toolbar is now active on our screen. The checkbox is checked, and we are good to go. You can also see right up here in the title bar the name of the application, the build date, which is today's build, and you will also notice that it says plus LiDAR, which confirms to me that I have an active version of the LiDAR module. Now, as with the other modules, or the other toolbar components, I should say, the LiDAR module toolbar can be undocked, can be dragged around, you can place it wherever you want. I'm actually going to clean my toolbar up a little bit by moving some of my other tools to the top level, so we can see all of the tools that are available in the LiDAR module. So I'm going to go through very quickly and describe what these functions, what these buttons can do, or what the LiDAR module at a high level can do. We're going to apply some of these in a more practical context when we go into some of our scenarios in a few minutes. But by way of introducing the module, let's take a look at some of the functionality we have now enabled. The first and probably the most obvious one is a drop-down that will allow you to change the visual representation of your point cloud. When Katrina imported that file, it defaulted to being displayed with the currently active elevation shader. And you'll see that represented in the legend on the left side of my screen. Whatever your active shader is, in this case it's the Atlas shader, that will be what is used to display each and every point. And I can change that even at this level if I want to choose, for instance, my global shader. Obviously, there's not a great deal of elevation range within this geographic area, but those are the colors that have been applied to my point cloud. We'll go back to Atlas shader again. Now, with the module activated, we have a separate drop-down that allows us to change from viewing by elevation to viewing by various other components or attributes of your point cloud. I'll show you some examples. So let's look at intensity. Some people have suggested that this view looks almost like a black and white photograph, and as it does. The return intensity of each laser pulse obviously is dependent on the surface that it's in contact with, and that variable is being used to provide visual contrast between each of the points. And you can see quite clearly the road, you can see some open area, you can see buildings. So in a sense, it does look like a black and white image. And we know our point spacing is, what did you say, just over a meter, just under a meter, I believe. So it's like a 1 meter resolution image that we're looking at right now. So it's just an interesting way of visualizing our point cloud. Another option here is to visualize by classification. Katrina showed us the metadata, and we were able to determine from looking at the summary of this data that there was about a 50-50 split between ground points and unclassified. And you can see that reflected now. I don't have a legend displayed. I could bring up a legend to show what those colors represent. But we know that our gray points are unclassified in this case, and our brown points are ground points. Now we're going to address this issue a little bit later. We're going to apply some different classifications based on some algorithms we'll apply to our point cloud. But in the time being, we can, as you can see from the drop down, simply change what's being used to represent each point in our point cloud. One of my favorites is return number. I'm sorry. Return number is a reflection of how many returns per LiDAR pulse. Typically, multiple returns will correspond with a surface that is not a solid surface, that's partly penetratable. I don't know if that's a word, Katrina, penetratable. Like a leaf. If a laser pulse hits a leaf, it will reflect a certain amount of that signal, but will also penetrate and hit a second surface and maybe even a third or a fourth surface. So a visualization based on return count is a good indication as to where there's vegetation. The blue points are the last return, so that's obviously a single point where there's ground, but areas where we saw some foliage, some vegetation, you can see there are multiple returns. I'm going to zoom in a little closer, and I'm going to use the same feature info tool that Katrina had used. I'm going to select one of my red points here, and you can see this is the second of two returns. So this particular pulse hit a leaf, perhaps, and reflected and then continued and probably hit ground, and that's the ground return that we're seeing right there. So visualizing by return number, again, different way of looking at the point cloud, different information can be derived, as you can see. Another visualization option, as you can see, is height above ground. Now, natively, this data does not have a height above ground value associated with each point. But if we select this option, what's going to happen is Global Mapper is going to actually perform a very quick ground analysis, and it's going to determine the height that each point is now above that created surface model. And if I select a point now, you'll notice we have that height above ground variable, that height above ground value. So different way of visualizing data using the same legend that we saw earlier, where our zero values now do not represent sea level, but actually represent a ground level.
And is that based on the ground class that it's calculating that?
Actually, that's generated dynamically. Great question, Katrina. We don't actually have a ground model per se, but what Global Mapper did during that very quick process is it looked to see which points were likely to be ground and created an arbitrary surface, if you like, and then calculated and subtracted essentially a known ground point from the maximum height from the known ground point, giving us that value. So we will formalize that process a little bit later, where we'll actually have Global Mapper assign ground and identify which are likely to be ground based on parameters that we establish. So you may have noticed in this drop-down list another option at the top. It says color LiDAR by RGB, and then it says or elevation. Now in this example, we don't have any RGB values inherently associated with this point cloud. It didn't come with any RGB, so there is no color value, so it defaults back to height by elevation. However, one of the functions that the LiDAR module provides is the ability to assign a color to each point in a point cloud. And for this, what I'm going to do is import some imagery. I'm going to import a little image file, very small little tile of some aerial imagery. I'm going to adjust my hierarchy here so we can actually see that that imagery and my point cloud. I'll zoom out just a little bit here so we can see the entire point cloud. So all I have here is a sample. I think it's nape imagery with our small little tile of LiDAR sitting right on top. In the toolbar, all the way on the right hand side, you'll notice a button that looks like an array of pixels. This is the function to add colors to a point cloud from whatever raster data that you have loaded or whatever raster data is sitting right underneath. I'm just simply going to click this button. There's no dialog box, it's just a status bar, and the result seems to be that the point cloud has disappeared. It actually hasn't. It's inherited the colors of the pixel that sits underneath each point. Now, imagery is an obvious use for this tool, but it can also be used with topographic maps. If you've got USGS quad maps and you want to derive a point cloud from the colors in those quad maps, or perhaps a utility map and you want to apply colors from your utility map to a point cloud, whatever raster data you have loaded, you can apply those colors to the corresponding points that sit at each pixel location. Now, I think the best way to illustrate this or to visualize this, first of all, I'll turn off my original imagery. Now you can see the points now have colors, again, that coincide with those pixels from that image. Bringing up the 3D viewer that Katrina showed us earlier, we can now see the point cloud in all its glory with fairly realistic colors now assigned based on this fairly low resolution image. So as you can see, it gives you a completely different context, a three-dimensional model, if you like, of a point cloud. Now I'm going to go through a scenario a little bit later where we're going to perform a filter based on RGB values that are assigned to a point cloud. So looking at some of the other buttons that are in the LiDAR toolbar, go back to classification here. I'm going to choose my classification visualization. Let's say we wanted to manually change the classification for some points. And this is not a very commonly used function, but it certainly is something that is available to you. As you saw previously, I have the option using the digitizer to select a point or to select a collection of points. I then have the option to edit those. I can right click using my standard digitizer edit function. It's going to bring up a unique dialog box unique to LiDAR where I can assign a classification based on the drop-down list you see here. I could also change the elevation and the intensity. I'm not sure when I ever would, but I do have the option to change those variables for every selected point. So the manual editing is certainly an option here. I can also simplify that process by using one of the shortcut buttons that you see in the LiDAR module toolbar. We have a button for immediately assigning ground, and this is simply a tool for assigning the classification. I'm going to choose an array of points right here in this unclassified area. I'm simply going to click this button, confirming that there's 721 points selected and they're all going to be changed to ground. Am I okay with that? I click yes. And we'll see now I have a little square of ground points in there. So simple tools for one-click reclassification. Ground, low vegetation, medium vegetation, high vegetation. We have buildings here as well. So if you've got a building footprint layer, you can simply select all of the points that fall within those buildings and immediately with one click reassign those points to be the building class, the SPRS building class. We have power lines and we've also got water. So these are the more common classification options available as a one-click function. Additional buttons in the toolbar are more advanced functions, which I've promised we will get to. Auto-classify noise, we have auto-classify ground, auto-classify non-ground, which is going to be buildings, trees, and power lines. And then we have our feature extraction function available as well. The final button is the same filtering button that Katrina showed us in the configuration dialog box. We can access it right here, perform the same filtering options, removing whatever classifications we don't want, or whatever return types that we're not interested in seeing. So those are the functions of the LiDAR toolbar. There are also functions that the LiDAR module enables that are not immediately visible. Functions that essentially are activated under the hood. Some of the speed improvements I've talked about, you will not actually see anything visibly different in the application, but the performance will be significantly improved for all of the processing of your point cloud data. Another one of those kind of peripheral changes is the ability to generate a cross-sectional profile of a point cloud. I think probably the easiest way to visualize this is to change our visualization back to RGB values. And I'm going to zoom out to the full extent one more time. The profiling tool, for those of you who have used it before, is typically used with a terrain surface. You want to do a cross-section of the terrain, or perhaps do a linear profile of a trail or a road, so you can see the increases and decreases in elevation or altitude as you go along that profile. In the context of LiDAR, it's a little bit different. Because LiDAR is a point data set, obviously we don't have a solid surface. So instead of simply drawing a linear path, what we do with this tool is define a swath or a buffer. And you, after selecting the profile tool, as you can see from my toolbar, you can right click on the map and specify the width within which the points are going to be profiled, or that lateral perspective, if you like. I'm set to 30 meters here. I'm going to bring that down to 20, and you'll see the results of that in just a second. We'll click OK, and I simply create my profile line. Now, the default profile line is that yellow line. The shaded area either side of that line is my buffer. Essentially, every point that's now within the extent of this rectangular buffer is going to be profiled. I'll simply right click. It'll bring up my profile dialog box. Apologies, it's on my second window. I'll drag it into view, and you can now see that cross-sectional view of our point cloud. Slightly exaggerated in terms of its vertical exaggeration, but it does accommodate the full extent of this window, as you can see. And these are, again, the same colors. You will also notice in this dialog box there's another array of reclassification functions. We can assign ground, vegetation, etc. We can change the visualization in this context. We can edit points, delete points, or filter points as needed. Now, again, we're going to come back and look at this tool in the context of a real-world scenario where we're going to do some data editing in it from a lateral perspective. There's one more function I want to show you by way of introducing the toolbar, and that's something that was added fairly recently: support for NIR, near infrared data in a point cloud. So what you see on the screen now is another point cloud. Now, this is a little bit of a different point cloud in terms of how it was collected. This is actually photogrammetrically, did I say that right, Katrina? Derived point cloud data. Essentially analysis of images from multiple angles, which was used to create a 3D model. It is a point cloud. It has the same characteristics as native LiDAR. If we zoom in close enough, you'll see points, but you can see the points are in a regular array. Unlike airborne LiDAR, where it's fairly irregular, this is a regular array of points. It's also very densely spaced, very closely spaced. If I go to my metadata, for this layer, you'll see the point spacing is 25 samples per square meter, as opposed to about a meter with the airborne LiDAR we were looking at before. Now, this point cloud obviously has RGB values natively embedded in the file. It also has near infrared data. And if I use my feature info tool and again look at a specific point, you'll notice NIR. You'll also notice we have NDVI and NDWI. The naturalized difference vegetation index has been calculated, as has then the wetlands index as well. So we can visualize a point cloud based on those two variables. From the drop-down list, first of all, I'll show you simply looking at the color infrared values. You can see this is an infrared visualization of that point cloud. Calculated from that color infrared value, we have our vegetation index. And you'll see the NDVI index on the legend on the left side going from -1 to +1. You can see within this range we only have minus 0.2 to about +0.6. Further up the scale you go, greenness increases. This is an indication of the health of the vegetation. More greenness, we would assume, would be more healthy vegetation. So from a raw point cloud, we can generate an NDVI index, as we can with NDWI, and this is going to give us an indication of water. There isn't a great deal of water. It's not actually, these are false water points here. But those two options are available if your point cloud is appropriately formatted. And in this case, the original data, oops, sorry, wrong one. The original data, when it was captured, I believe this was captured by an unmanned aerial vehicle, which also had an NIR camera or a sensor built into it. So it captured this data in real time, and it was attributed to each point. So again, this is a function, a different visualization, and certainly a different analysis tool that's available with the LiDAR module if you have the appropriate data. Okay, so now that we have introduced the toolbar and the primary functions of the toolbar, what functionality the toolbar brings to play in Global Mapper, we're going to spend a little bit of time going through some very specific scenarios that apply some of these tools in fairly real-world situations. Most of the data we're going to be working with is actual data that was sent to us or provided for us for a particular reason, and certain data needed to be processed in certain ways, and so these are obviously real situations. First set of challenges, first set of scenarios, we actually got a couple. We're going to talk about some of the filtering options, a couple of the different filtering options that are available over and beyond simply turning on and off classifications or return types. So on the screen, we have a sample point cloud. This is, again, a fairly high density point cloud showing an area where there's been a landslide. And the folks who provided this, one of the issues that they had to address was the fact that the surrounding area where they were going to derive a ground model had a lot of vegetation. We have tools for identifying vegetation, which we're going to demonstrate in a few minutes, but in this case, the vegetation is very low vegetation. These are little bushes. So they wanted a way to remove these bushes. Katrina, you're going to go through a scenario here. We're going to see one option there is for performing this type of filtering.
So we're coloring right now based on the RGB, so imagery of the area. And you can see that the bushes themselves have a pretty distinct color from the surrounding terrain. So that's actually one way that we can do some advanced filtering to pick up on those, because they're only slightly higher than the ground around it. So using that poly selection tool that we saw before, I'm just going to select this rough area that contains some of these shrubs that we want to identify. And then by right-clicking, I've got the editor tool on right now just for clarification there. We're going to go down to advanced selection options, and we've got this whole set of additional filters that we can use beyond just the class or the return type. So this is specific to the LiDAR module.
And this is perhaps one of the more hidden components of the module, given that it's buried kind of in the digitizer tool, because essentially you're interacting with the digitizer. We want to make sure you're aware that this is here. And again, recapping, it's a right click with the digitizer, advanced selection options. It'll give you this dialog box.
Yep, and it's working based on an existing selection already. So within this region, one thing that I could do, as I was mentioning, those bushes are quite green compared to the surrounding area. So one thing that we could do is use the color filtering option. And I've enabled that, and right now we're just starting with a base RGB roughly close to our bush area, and then using this filter slider, I've grabbed some of the green range around that. That's what this fuzziness is doing.
Fuzziness is the term we often use. It's not a specific color, but obviously a range of colors.
Yeah, so many shades of green that we want to capture here.
And it's sometimes the best method for applying this is trial and error. You'll also notice, by the way, without taking too much time, that the other filtering options that are available here in this dialog box, you can see filtering by elevation, filtering by return type and return class. All the way over on the right side, we have some very advanced filtering by angle, by intensity. So if you want to keep your certain intensity ranges, and then we've our NDVI and NDWI values if you want to filter your data to isolate NDVI, the index values within a certain range. This is a way to do it. This is a very, very powerful component of the application.
Yeah, you could see from the coloring by some of those attributes that those were some really good ways to identify features within our LiDAR data set.
And I should also say, and you'll see the results of that. I'm kind of spoiling the plot a little bit here, Katrina, but you'll see this is we selected a group of points to begin with. When you apply the filters here, it's going to apply the filter to the selected points. So what's going to happen is it's going to retain the points within this selected area that adhere to the filtering settings that you've applied. And you can obviously apply more than one type of filter. You can do elevation as well as color, or any combination, classification and color, or classification and elevation. So really the sky's the limit as far as options are concerned.
So let's see how it does at finding those shrubs. Let's zoom in a little bit. And this is a much better way to see that we've done a pretty good job here of picking up some of these areas of shrubbery. And something I might do now is just automatically assign those the class of vegetation.
Yeah, low vegetation. And if the intention is to do filtering, and I will go ahead and do that, if the intention is to ultimately filter these out by applying a unique classification. It looks like you grabbed about 82,000 there in one fell swoop. By reassigning the classification in this context, obviously it gives you the means then to go into the standard filtering dialog box and remove low vegetation, or remove everything but low vegetation, depending on what your workflow is. And to verify that actually worked, I'm listening for a roll of the drums in the background here. Yeah, we go, visualizing my classification. We now have very clearly defined where those little low-lying bushes are within this area. That's a very, very cool tool. Obviously the initial filtering, but also allowing simple editing in this context as well.
I could have also chosen to delete those points
if you needed to do that as well, absolutely.
Wanted to cut them out.
Just the delete button on your keyboard would have done that, so great. So another filtering scenario we're going to show you right now, and this is another little sample of some data. This is actually relatively close to where we are right now. This is just up the road in the main capital, city of Augusta. And we've got a little point cloud data here, which you can see right in the middle is we've got the river visualizing by elevation, as you can see. It may be visible. I'm not sure if this is actually going to work, but we'll try. I'm going to bring up a 3D view. It did work. These are the birds that we were referring to. You will notice in this point cloud, and this again, as I said at the start, this didn't take a lot of intense research. This was the first sample I grabbed. You can see obviously there's a little bit of noise here, a little bit of erroneous points. These are obviously something you could remove manually, but we might as well use the tools at our disposal. We're going to filter this data to remove any excess points that are beyond the known range of the data that we're working with. That's both above ground, also below ground, and this is probably more applicable because you'll notice a number of returns here in the river area. And if I go back into my 2D view and I select one of these returns, I'm just going to use my feature info once again, you'll notice these are all technically below sea level. It's obviously picked up a return from the bed of the river. This is identified as a ground point. Simply because of the nature of the return. So we don't need these. We don't need to imply that there's ground where there's actually a riverbed. So again, we will want to use the filtering tool to get rid of this noise, to get rid of those points that are beyond the extent of what we're interested in seeing. Now, number of ways of doing this. The filter dialog box that Katrina just showed us has options for removing points above and below a certain threshold. You could also go into the options for this layer and again limit the elevation extent of the point cloud. But I'm going to show you a brand new tool that we've added, indeed a brand new button in the LiDAR module toolbar, auto classify noise points. Now I think to see this more easily, we'll turn on our classification visualization. And as with other data sets we've worked with, there's really only two classes visible here. There are ground points and there are also unclassified points. In this case, what we're going to do is we're going to assign a new classification, and we'll see the visible results of that when we finish this little scenario. So we've only got one point cloud, so this is all that we're analyzing. We want to apply the certain noise classification parameters by defining the maximum allowed variance from a local average. And I've put in 3 standard deviations here from my local average. Anything beyond that is going to be flagged, and ultimately, if necessary, it can be removed. I'm also going to define the extent. Now you see 2 options here. One is based on ground height. I'm not worried about that in this case. I'm going to filter based on absolute elevation or elevation above sea level. Now as you can see, the low point, and this is actually picked it up from the data. The low point in this point cloud is actually minus 24 meters. There is no minus 24. We're not in Death Valley here. We're not below sea level, at least not I'm aware of. So this is obviously an erroneous point. Also, these points that we identified as being on the riverbed, we want to get rid of those as well. So I'm going to establish a very defined threshold of 0 as being my cutoff. Everything below 0 I'm going to assign as noise, stuff that I don't need to address. You'll also notice that the maximum is 400 meters. Well, I'll tell you for a fact that there is no area in the vicinity of Augusta that's 400 meters above sea level. That's that bird or plane, perhaps? I don't know. Maybe that's that erroneous point that we saw floating in the air. Again, we want to get rid of that as well. I know for a fact that the maximum elevation, even of the tallest building, I think it's the Capitol building, is about 65 meters. So I'm going to bump this to 70 meters. Everything outside of this range will be removed. I have an option here to mark these noise points withheld or deleted. So in other words, if I'm not interested in simply reclassifying, but rather just want to remove them completely, I can check this box. In order for us to visualize the results, I'm going to leave this unchecked. And we'll go ahead and simply click OK on this. And again, to clarify, this is a reclassification tool. We're asking Global Mapper to apply a new classification to points that adhere to the parameters that we've established. I click OK, wait for it to go through the process, and you'll see quite clearly here that we have, obviously the points that occupy the areas below 0 are now flagged as noise. We can very easily filter those as we would with any other point. Also, I'm going to try to find those couple of points that were way above. I think the easiest way for me to do this is to turn off my ground and unclassified, and hopefully we'll see those guys as well. There's one right here. And if I use my feature info, yeah, 400 meters above ground. We've flagged that one as noise. At this stage, if I just simply want to get rid of them, I can perform the filter or just simply delete them. I could have done that during the process. I can do it now by simply selecting and deleting. So that's another very, very powerful LiDAR QA, LiDAR editing, LiDAR processing tool that lets you filter data based on elevation thresholds. Okay, so those were just two examples of filtering options that are available to essentially clean up your data. We're going to move into a couple of scenarios where we're going to address what I define as applying intelligence to your data, automatic point cloud classification. And we're going to go through actually 2 or 3 simple little workflows where we're going to take some very raw data. Essentially what I've done with a point cloud was remove all inherent classification. We're going to have Global Mapper identify based on simply on the geometric characteristics of that point cloud which points are likely to be ground, vegetation, buildings, etc. We're going to go through a little scenario to identify those points. We're also going to go through and look at a power line classification scenario. This is a brand new function in Global Mapper 17 with the LiDAR module. So we will identify, again, within some unclassified points, a linear array of points that represent a power line. Okay, so here again we're using another very small point cloud, a fairly low resolution point cloud. This is an area of suburban Portland. We're visualizing by elevation, as you can see. I'm going to change the visualization to visualize by classification. And as you can see, all of the points in this point cloud are unclassified. I removed the classification so I can show you the reclassification functionality. This brings to play some of these buttons that we referenced previously in the LiDAR module toolbar. Specifically, we're going to look at auto-classifying auto-classifying ground points. We'll address the non-ground points in a few minutes. And if I select this button, it's going to bring up a dialog box that allows me to establish the parameters by which Global Mapper is going to identify within this point cloud which of the points are likely to be ground, which are likely to be non-ground. And it will ignore the non-ground ones, leave those unclassified. We'll address those in a few minutes. For my ground points, as you can see, there are certain settings that can be applied. First of all, we need to define an area, geographic area within which it's going to analyze the distribution or the array of points. That array can be based on a multiple of the point spacing, the average point spacing within this point cloud, or a specific distance in meters if you like. Now in this scenario, I'm going to bump this up just a little bit. I'm going to establish a fairly large area, 5 point spacings. Again, it's going to look within that area for a pattern in the points that it can define as being a ground surface, a relatively flat area. I'm going to jump to the bottom of this dialog box. Sorry, Katrina.
Yeah, so I was just going to say sort of the basis of this algorithm. You can see it's not expecting ground to drastically change, right? So that's sort of what we're looking for with these settings.
That is the general rule, absolutely. And there are certain situations in which we've had to tweak some of these settings at the bottom in steep terrain.
Yep.
To identify those ground points. So certainly in this situation, this is a urban area, relatively flat, so I don't think we're going to have any problems. But as with other scenarios, by the way, I have found trial and error is the best approach. If you're not getting the results you would expect, you can come back and tweak some of these settings to
looking at Yosemite settings.
Perhaps. So that's a classic example. Or even I was looking at some data of a hillside where there was a fairly steep cliff, and again we had to tweak the settings a little bit to actually identify ground so we could measure the volume of material that had been displaced in that hillside. The two settings at the bottom allow us to establish maximum known height and maximum or expected terrain slope to reflect what you've just suggested, where you can define the known parameters. Anything beyond these will be ignored. So if I do have a skyscraper, or if I do have perhaps the side of a building which is a very steep slope, maybe an angled building, it will disregard those if it's beyond this slope angle that we've defined here. These values will work in this context. I think perhaps what's more important is this value, because we can establish a vertical threshold from known ground where each point needs to be considered ground. It's currently set to 0.3 meters. Again, because of the point distribution in this case, I want to bump this up to 1 meter. Now what this is going to do is every point that's within 1 meter vertically of a ground plane is going to be assumed to be ground. This is a pretty high threshold. With a more dense point cloud, you may want to keep this value a little lower. You're going to get a much more precise model. But in order to get enough points, we're going to keep this a little high in this case. Again, those points that are beyond a meter from known ground are going to be disregarded. They're going to be still be unclassified. And that includes buildings. Obviously, buildings would represent a flat surface. At least some of these big box stores you're going to see in this example, these large retail stores, they would have a flat surface, but because they're above a meter above known ground in the area, they will be left unclassified. So with these parameters established, we'll simply click OK, and we should see immediate results where our point cloud now has been assigned a different set of colors to reflect the new classifications. And if I go to the metadata very quickly, oops, my overlay control centers migrated again. If I go to the metadata, you'll see, I believe in this case, it's almost exactly a 50-50 split again, based on the distribution of ground. We created 800,000 ground points from nothing, from no classification, based simply on the algorithm that we applied. And it's very easy at this stage to identify buildings, and again, vegetation, and we're going to address those individually when we do an extraction process or we do another level of classification. I should also say this is far from being a perfect science, and I use this example for good reason, because you can see there are anomalies. This building right where my cursor is located, over here towards the left side, you can see has been identified as ground. We know it's not ground. This is a very large retail building. I believe it's one of those big box hardware stores. And you can see in this case, because of the size of the building and also because there are protrusions or objects on the roof, Global Mapper saw that pattern of points and assumed it was a ground surface with trees, I believe. We will address that specific issue in just a minute, essentially a manual override of the automatic classification process. So I just want to illustrate, again, far from being a perfect science, there is a little bit of tweaking and manual QA that will have to be done to your data. So automatic detection of ground, automatic ground classification. If necessary, I could turn off my unclassified, create a surface, and I know with confidence it's a very accurate ground model or a terrain DTM, digital terrain model. So the next extraction process, kind of following on, is to look at these points that remain, these points that are still unclassified. Again, we know that there are buildings and we know that there are vegetation. And the next button in the LiDAR toolbar allows me to address those remaining points in my point cloud. Bear in mind that before you perform the action I'm about to show you, you need to have ground assigned. You need to have identified these points that are actually ground in order for the next phase to work. You'll notice this dialog box has a couple of options. Below you'll see power line classification. We're going to get to that one in a couple of minutes. We're actually going to go through a power line classification workflow. For the time being, we're looking at buildings and vegetations. This is kind of the suburban identifying non-ground points that are trees or buildings. This is a very common use for this tool in the context of suburban Portland, as I'm showing you on the screen right now. So I'm going to check that box. And again, we can define our bin size to check for points, these remaining unclassified points that adhere to either being buildings or being vegetation. Some of the parameters that we can establish, again, we can define a minimum height above ground. In this case, we've established 2 meters as our threshold. I'm just going to verify that this is actually the value that we want. I believe it is. Again, I've used this data set a few times. I want to make sure my parameters are correct. So 2 meters is going to be the threshold. In other words, any point that's 2 meters or higher is going to be addressed as to whether it represents vegetation or whether it represents a building, or if it's an anomaly, it will remain unclassified. Points that are below 2 meters will remain unclassified regardless, simply because we're assuming most buildings, most trees are below that height, below that elevation.
And so that's 2 meters or above or below the surrounding ground points?
Absolutely. So this is, we're relative to ground now. It's 2 meters below the ground model essentially that we've created. Global Mapper will look at that pattern and identify, again, the points relative to surrounding ground. This is not absolute, but this is ground-based. That's a great question. The coplanar difference allows us to define how far off a flat surface a point can be to be considered part of that surface. In other words, all of the points that occupy a plane it's perhaps a horizontal or an inclined plane. We're thinking of a pitched roof or a flat roof. If they fall within that plane to a variance of plus or minus 25 centimeters, they will be considered part of that roof section and will be classified accordingly. So we can keep this tight if we want to be more precise, or loosen it up a little bit again in situations where our point density is a little bit lower and we're not getting the results we expect. Vegetation distance offset as well, 0.4 meters in this case, I believe is the distance I'm using. Represents the offset between non-planar points, in other words, points that are irregularly positioned that would constitute obviously a tree which does not have a flattened surface. How far apart as a minimum value do they need to be considered a tree? And the angle difference as well as another option. How much of an angle difference between the planes of a building, in other words, the flattened roof sections of a building, to be considered a single building structure. Now, with these parameters established, and again, I believe these will work in this context through trial and error, haven't done this before. If I simply click OK, it will go through and address the 800,000 or so points that are still unclassified and automatically assign them to be either buildings or trees, or for that matter, leave them unclassified. The ones it's not sure about are still unclassified. But as you can see, with a couple of simple clicks of my mouse button, I was able to significantly improve the quality of this data. I'm confident now that I have vegetation isolated, I have buildings, and I have ground. I can filter, I can perform whatever analysis or processes I want based on that assignment. So the reclassification process is a fairly automated and a very, very powerful component of the application. Now, before we wrap this section up, there is one thing I want to look at again over here, and that's the building where we saw the points that were incorrectly classified as ground points. You'll notice around the edge there's also a number of unclassified points at that periphery. We know this is incorrect. We need to manually reassign these to make these actual building points. I could do a manual selection in this, just simply outlining them, but I don't believe that that's actually going to give me the results that I want, because there are genuinely unclassified points. I think they're representing air conditioning ducts. I don't want to make them part of the roof. So instead of manually selecting these in a two-dimensional top-down view, what I'm going to do is use our profiling tool. And I'm going to define a profile width, as we showed you earlier. I believe about 45 meters in this case is going to work. And I'm simply going to draw a line right through that building, encompassing all of those incorrectly classified points. And you can see now very clearly we have an array of points representing the roof that are assumed to be ground, which we know are incorrect. Those of you familiar with this type of structure, this I believe is actually a Home Depot. This is the greenhouse area for the Home Depot over here on the right side. You can see the roof pattern. Any of you have been to a Home Depot will probably be familiar with this. They keep all the outdoor stuff in under these canopy roofs. And you'll notice Global Mapper incorrectly assumed this was vegetation. It looks like an array of points, it may be a tree. So we could manually address that if necessary. It's not really relevant in this case, but we could also modify those points in this context as well.
And over on the left side there too, from the top down, it looked like those were incorrect, but those seem to be, maybe there is some vegetation on that side
Perhaps
of the building.
They have some trees growing there or something. Yeah, absolutely. It looks like it is a very irregular array of points, as you said. Now, very quickly, we can modify these points. This is not only a viewing tool, but it's also an editing tool. I'm simply going to draw a box around what constitutes the roof section that I want to reclassify. You'll notice I've left the protruding sections alone. I don't know what there's some anomalies up here as well. Maybe these actually may be trees that are beyond the extent of the building laterally, so I might maybe picking something up that's off the edge of the building. In any case, I'm not worried about those. But these points, which constitute a roof section, I can simply click the building button right here in the toolbar. 5,545 points will automatically be reclassified based on that. We'll close this dialog box. From my digitizer, I'll hit the escape button to deselect them, and you'll see quite clearly we have reassigned. You'll also notice that those air conditioning ducts are still unclassified. There's little gray blobs, which means when we create our building model, it will be based on the flat surface and will not factor in these protrusions. So that lateral perspective gives you a very, very simple but very effective way to edit data from a cross-sectional perspective. So another reclassification scenario we're going to take a look at, brand new in version 17 of the LiDAR module. In fact, this was not in the original release, I don't believe, Katrina. I think it was a more recent build.
Correct. The LiDAR module for version 17 was just released about 2 days ago, I believe.
Mm-hmm. There were some preliminary tools, but yes, if you're interested in the LiDAR module, we do recommend you get at least today's build or one of the current builds whenever you're viewing this, obviously. Go to our website. The online version is being updated continually, so grab the latest version. If you're one of those great customers who downloaded right after we released, you may want to update your version because you may not see these tools available. This scenario, obviously you can see there's another point cloud, and this is a linear point cloud, about 200 meter width swath here, and if I turn off the point cloud itself, you can see it follows a power line, a very one of those high density or overhead cables. I think the easiest way to take a look at this is to use our profiling tool again. I'm going to make sure my width is correct. It's reset to 30 meters, which is probably okay. So I'm just going to quickly draw a profile along a section, and you will see that this is a power line. We have some power line data. And our objective here is to identify these linear points and reclassify them as power lines, one of the recognized LiDAR ASPRS classifications. And as we go finalize this scenario in the next section, we'll actually extract these as line features, as linear objects, or as linear features in Global Mapper. So obviously in this case, we're dealing with a much higher density point cloud. The 1 meter resolution we looked at before simply would not pick up enough of these point clouds. Points in this point cloud. If I look at the metadata,
yeah, those power lines are pretty skinny.
They are
there compared to buildings or
exactly.
something like that.
As you can see, we've got 44 samples per square meter. In this case, 44 points for every meter square. So obviously, is much higher likelihood that the points will be reflected off power lines. Again, as I said earlier, do not expect the same results if you're using some of the lower resolution point clouds that are available on some of the online sources. Obviously, in this case, this point cloud was collected on specification for whatever the power agency or the authority is overseeing these power lines, and obviously they created a point cloud with the required density. So again, this is a reclassification process. I have, by way of preparation, already identified ground points, and you can see the vast majority of the points in this area are ground. If I turn off the ground points temporarily, it's simply because of the point density. It's difficult to see if there's anything left in there. But if I turn off ground, and I'll just apply that, you should see that there actually are a number of points remaining. Very specifically, you can see these long lines. These are the power lines themselves. This is what we're most interested in this context. So we will be addressing that in this process. We've been in this dialog box before. Let's revisit it again. The auto-classify non-ground points. Previously, we used this to identify our buildings and our trees, which we will revisit for extraction in a few minutes. Now we're going to go to the power line classification setup. And you can see, again, there's a specific set of parameters that we can apply to help Global Mapper identify power lines in this case. Height above ground, what's the threshold? And again, we're talking about ground here. We're not talking about actual absolute height above sea level or elevation above sea level. So you should see, if you're administering the power lines or overseeing the power lines, you should know they should be a required threshold. We'll leave that at 4 meters. So everything below 4 meters will remain unclassified, regardless of whether it's a linear feature or not. Minimum distance from a best fit line. So again, Global Mapper is going to identify a linear array of points. Those points that are within a meter of that threshold, above or below, are going to be assigned to that linear feature. That's a pretty high threshold in this case, and we want to see the results. So we'll leave it at 1 meter. And again, bin size to check. We're going to look at a 1 meter square, a series of 1 meter square to identify those linear patterns. And maximum height change per meter. Obviously, in the context of the power lines we're looking at right now, you saw from that profile perspective, they weren't horizontal lines, but rather they dipped between the pylons. And we can factor in what that offset per meter would be. And this is a fairly high height change per meter value here. Again, we want to make sure we're collecting enough points in this scenario. Now, because this is a very high density point cloud, processing of this data may take a little longer. So to quicken it up a little bit, I'm going to limit the extent of the analysis. You'll see, by the way, the Point cloud rendered in this dialog box appears to be at a different orientation. Reason for that is in the main map view, I adjusted the map rotation so it follows the horizontal aspect of my screen. In the selection window, obviously, it's reverted back to being north up again. So this is the actual alignment in terms of actual real world coordinates. I'm going to select just a small area for this process, just using this manual selection process. We'll click OK. So we've essentially populated these coordinate parameters with the manually selected box. Again, limiting the extent of what we're analyzing here. We'll simply click OK. Everything else in here is fine. Again, we're disregarding buildings and trees in this scenario, looking just for power lines. We'll click OK. You'll see it's going through looking for those within the height thresholds that I've defined. You'll see a number of dialog boxes here. Shouldn't take too long for this to process. But again, because the point density is a little bit larger, it's taken just a little longer to find these points, to identify these points. You'll notice it's interesting to read some of these dialog boxes. That one was calculating height above ground. Now it's applying the classification, and process is completed. You don't actually see anything in this view. Again, when I went through the scenario first time, I said, well, gosh, nothing happened. Again, the reason for that is because the sheer magnitude of points in this point cloud, the reclassified points are still being obliterated by the ground points simply because of their density. We could just quickly turn off ground and turn off unclassified, and we'll apply that, and you should then see those linear patterns. You'll see a few anomalies in the bushes on the side. We're not worried about those in the time being. Those are easy to remove, but you'll see these line features now quite clearly displayed. Perhaps the best way to view these, once again, is using our profile tool. I'll simply select the profile using the same parameters as before. Just do a short little profile section, and you should then see quite clearly we now have these power lines delineated. I think we were maybe a little low here above ground. We probably should have limited that. We lost a few points along the edge here because they were below our threshold. But again, this is a learning process, a trial and error process. We would know next time to do it based on more precise values.
So this dialog too, you could use to kind of figure out those parameters. We can see we're close to the
absolutely. That's a great scenario. We could also manually override. Now, people often say, well, why don't you just reclassify them in this context? Well, that would be fine if you could define very clearly what's a power line. If you had trees all around this, it would not be possible. In this case, it may be possible to reclassify within this dialog box, but obviously the automated process where it identifies those linear features is much more effective. So the next bullet, the next section in our module scenarios list is feature extraction, and it follows on from the point reclassification that we had done previously, both for our trees and building point cloud, and also for the power lines that we just worked in. So we're going to go through a couple of scenarios where we're going to create vector representations, both for the buildings we're going to create polygons. For the trees we're going to create points. We're actually going to represent those points with three-dimensional models. And for the power lines we're going to create line features. So we're back to our suburban point cloud where we had previously assigned our classifications. And we're going to identify a couple of different things. We're going to identify buildings. I'm going to do that one first. You can obviously see where the buildings are. We can see these large rectangular features. I'm going to focus on this particular building for this scenario. I'm going to zoom in a little closer. We can see the results of this. Let me again use my zoom tool, and we're going to run through a vectorization process where we're going to identify, based on these reclassified points, where our buildings are located. This feature extraction tool is another button in the toolbar. This is the final button in the LiDAR module toolbar. And again, this encompasses a couple of different scenarios. First of all, buildings. We also have our trees and our power lines. I'm going to uncheck the power lines option. We'll get to that in a few minutes. And we're going to identify buildings. We're going to have Global Mapper look for buildings. Once again, this is a situation where the higher the quality of the data, the higher the resolution of the data, the better the results. Now, in truth, this point cloud is a fairly low resolution point cloud, so we're not going to get the precision in terms of precisely aligning the building footprints as perhaps you would like, but we can do a little filtering, a little QA. We can assign a simplification multiplier. In other words, we can remove unnecessary points to create essentially straight edges along our buildings by applying a value in here. And once again, I find that trial and error is the best ploy for determining what this value should be. Sometimes I use 4, in this case I'm going to use 5 so it really smooths out these building angles. The options right in here in the middle are mostly related to creating building models with roof planes that are offset. You can see angle difference and distance between planes. Now this would obviously be most applicable when you're dealing with pitched roofs, where obviously one side of the roof is angled in one direction and the other side is in another direction. Rather than defining those as 2 separate buildings, using the parameters that you have here, it will consider those to be one building object. It will delineate as a single building object. And again, I don't have the resolution of the data that would support that type of differentiation, so it's not really relevant in our case. So again, all we're dealing with is buildings here. We'll click OK, and should not take too long. We'll see a new layer created, and if we turn off our point cloud, you'll see it has delineated the outline of this building. You will notice a little bit of an anomaly here, and if we turn off the vector layer that's just been created, you can see why. This is actually, I believe, a loading dock that is within the threshold of what was defined as the roof of the building, and you can see it's actually accommodated that. Now, because this is a vector feature, it's perfectly easy to simply modify that. I don't have my vertices enabled, but if I did, I could simply take that vertex, remove it, maybe clean up the angle here a little bit. But you can see the rest of the building is a fairly rectangular feature. If I use my feature info tool, you can see that building is actually a 3D building. It's got a height, and it's also got an elevation. Height is based on its size, its height relative to ground, and elevation is obviously absolute relative to sea level. You also notice the maximum and minimum thresholds as well. So this value right here is a fairly precise value in terms of determining its height. I've done some experimentation with known buildings and run this analysis, and it's usually very, very close in being able to determine the actual height of the building. And just to verify what we've suggested, if we go into 3D, we will see this as a much exaggerated 3D building. Let's bring this down to a 1-to-1 exaggeration, and that's a little more realistic. We can now see that big box store as a 3-dimensional model. Again, derived, if you think back to where we started, from a completely unclassified point cloud. We identified buildings as a separate class within our point cloud, and we're able to extract those as a vector object, as you can see. So continuing with this data, and continuing with the reclassified points that we were working with previously, I'm going to now identify or try to extract vegetation points, specifically trees. You can see this is a residential area, some small buildings over here. We're not concerned about those, but obviously next door there's a forested area. If we use our profile tool and we draw a quick swath through, you can see there are trees, there are vegetation. This is high vegetation, looks like from 20 meters to 50 meters, about 30-meter tall trees in here. So they're fairly large trees. You can see our ground points clearly defined here as well. What we want to do in this scenario is not simply identify which points are trees, but what collections of points constitute a single tree. We're going to identify individual trees and essentially assign a point for each of those individual trees. Using the same dialog box we were visiting previously, this time we'll deselect the building extraction and look for our tree heights. So again, extracting tree points, establishing a minimum tree height. I'm going to bring this down just a little bit. Let's just bring this down to about 4 meters, approximately what, 12 feet? Maybe we'll bring it up a little bit. Maybe we'll just limit it to those who are a little taller. Let's do a 5-meter threshold. So again, any of these vegetation points that are under 5 meters will be disregarded. They will not be considered as part of these tree models. We can also establish tree spread thresholds, minimum and maximum. Minimum spread, as you can see, is established at 7 meters, maximum is 20 meters. So again, this will allow us to define more precisely the geometric properties of our tree. You will notice another checkbox here that we can use to create coverage polygons. This is a great tool, but it's not one I demonstrate a lot, quite simply because it creates a mess. Every tree that we're going to create has a polygon, and a regular polygon that defines the extent of its spread, and it just creates a lot of overlapping stuff. So it's great, it's useful, but aesthetically it makes your map look messy. So I'm going to remove that or leave that unchecked in this scenario. I think we'll leave everything else as it is. Again, we'll click OK. This is going to generate another vector layer. It's an extraction tool. Easiest way to see this one is to turn off the point cloud once again, and I'll turn off the underlying imagery, and you can see we now have individual trees. Each one of these trees, if I select it with the feature info tool, has a height. That height is height above ground. It's got an elevation, which is absolute elevation above sea level, and it's got the average and maximum spread as well. So we've just conducted a tree inventory within this area based again on a simple raw unclassified point cloud. Because these are vector points, like every other vector layer in Global Mapper, we could perform an analysis. Katrina brought this dialog box up earlier in the context of some point cloud data. Here it is in the context of these tree points that we've created. I'm going to sort by height. I'm just selecting the columns, and we can see all of these trees at the top are now over 30 meters. If I was only interested in trees that were 30 meters and above, I'm holding down the shift button on my keyboard, just simply selecting those. This is a manual process, and you can see where those trees are located. So we've done an inventory of our forests, and we can see where the tall trees are if we're interested in harvesting or preserving. If that's the case, you can see that's very, very easy. And again, I have to remind you, this was derived from simple unclassified point cloud data. Now, the final part of this scenario, extraction for our trees, again, we're going to get a lot of oohs and ahs coming from the gallery here, is the visualization of these in a 3D situation. We've just introduced support for 3D models in our 3D viewer. And as you'll see, these actually look like real trees now. We're actually looking at models of trees. There's actually a couple of different variations on that theme. We have an evergreen model, we have this deciduous model, and you'll notice there are different sizes, and that reflects the size variables that we used to do that extraction process. So you're looking at a realistic perspective of the forest as a collection of 3D models in this 3D view.
So those models are being scaled based on the attributes of the points that you just looked at?
Specifically the height, yeah. So we're looking at, again, if we did a quick analysis here where we identified those trees that are over 30 meters, we would see those as being the largest models in here. I'm not sure that the deciduous model in this case is necessarily the best choice. These are mostly coniferous trees, I believe, in here, so we can change that. We could reassign a different model, and you can also bring in your own three-dimensional models, by the way. This is aside from what we're dealing with today with the LiDAR module. With version 17 of Global Mapper, we introduced support for using three-dimensional models to represent point features. Go back and look at our Introduction to 17 webinar, and you can see how that process works. Okay, and second of the extraction, or I guess third of the extraction scenarios, coming back and visiting our power lines once again, where, to remind you, we had reclassified these power lines based on the linear pattern, above ground linear pattern. We can run the extraction process on this data again as well. Same dialog box we looked at previously. Not doing tree extraction in this case, but rather we're doing our power line extraction. And once again, we have parameters that allow us to establish what pattern of points are going to constitute a linear feature. Distance between best fit line, once again, can be established. Maximum angle delta that you will allow, in other words, the angle of the power line, and also the minimum power line length. In other words, you may have a small array of points, perhaps in a tree or something, but if it's within below a certain distance threshold, we'll disregard it. I would tend to keep this value fairly high, just so you know. Obviously, most power lines will be fairly long, so you'll guarantee that the only linear array that you'll actually capture are the power lines. Again, we'll leave these defaults. Once again, I'm going to limit this to a relatively small geographic area, and we will hopefully see the results of this fairly quickly. Click OK, and once again we'll click OK. Going to be difficult initially to see. I think we actually can see those lines right now. I'm going to turn off my point cloud and zoom in just a little closer, and we will go ahead and pop this up in our 3D view, and I think this is going to provide us the best visualization of these line features that we captured. Let's bump up our exaggeration. Obviously not quite as tall as that, but you can see we've now captured lines. A few little anomalies here in the bushes, but they're again very easy to remove. But we now have line features that were derived from unclassified point cloud data. And you'll notice a few little gaps. We have tools in Global Mapper, vector modification tools that let you join lines together very easily. You define the distance thresholds and it will connect your lines very easily. And you'll also notice that these are 3D lines. All the vertices in these lines have precise elevations because they're not obviously adhering to the ground. They are alternating based on the alignment of the power lines above the ground as well.
Okay, so the last thing we've got on our list here is going back to creating an elevation grid from our LiDAR points. So we saw that a little bit with the LiDAR module disabled, but we're going to take a look at that now with the LiDAR module.
And I think what you did, we probably didn't go into enough detail, what you did with the LiDAR module disabled, you created a tin-based surface model where all the points were triangulated. Now, granted, it was a small point cloud, but that usually takes a little longer. Different process as you're going to show us right now.
Okay, so we've got that same Gardner data set loaded up again that we were looking at previously. And now if we wanted to create either a digital surface model or a digital terrain model, we can do that. So now under the gridding method, we've got these options to create a DTM using the minimum value or a DSM using the maximum value. So let's go ahead and start by trying to get just the terrain here. And then just go ahead and call this layer DTM so we can differentiate there.
And you'll notice a point spacing variable down below. When you're running a binning process, you basically have to define the size of the bin, as we did when we were doing our extraction exercises. So by leaving this at multiple of two point spacings, it's going to aggregate the surface, it's going to speed up the processing significantly, and ultimately it'll give you a much more smooth surface model.
Okay, so let's go ahead and run that. So that's our digital terrain model.
Yeah, that's removed. Essentially, it's taken the minimum value within those bins.
So now let's turn on the LiDAR again and see what happens when we look to create a digital surface model. Okay.
So you created two models here, basically variations on the theme based on a 2-point space. And I think we had, 1 point per square meter? So it's about a 2 meter square. Within these 2 meter squares, we first look for the minimum value, and then we look for the maximum value to create our DTM and DSM. Now, you'll see, if I use my image swipe tool, you should see there is a difference between the two. The DTM, which is underneath, reflects ground. It looks like these are ground models. The minimum point within those bounds is going to be picked up, and you can see it's obviously a much more precise ground model. This is a surface model, so it's just capturing the trees, the canopy, the structures, everything that's above ground. Another way of visualizing this is to use our profiling tool. Now, because we're not profiling a point cloud, we don't have a swath to define. It's just going to be a simple linear path. Just going to draw an arbitrary line, and you'll see two lines represented here. You'll see the DSM, which is the red dashed line as indicated by the green shaded area. You'll also see the DTM, which is the ground model indicated by this blue line. There's a little bit of an anomaly here where there obviously didn't pick up any ground at all. So maybe a filtering process would have been a wise choice to do here as well, to remove non-ground points. But the two variations that Katrina demonstrated, DSM and DTM creation, are again much more precise and certainly much faster terrain surface generation processes than would be available without the module. So hopefully the last few scenarios give you some information about the capabilities of the LiDAR module, which brings us to the question we started with. Do you need the LiDAR module? Is it required? Well, let's go ahead and we'll take a look, a summary of what you get with the module and what you get without the module. As you can see, the first three items there, simple reading and writing LAS and LAS. By the way, we didn't do any exporting, but whatever processing that you have applied to your point cloud, you can also apply to the LAS files themselves. You can export LiDAR, in other words. You can do some basic filtering, as Katrina demonstrated, and you can obviously generate a terrain surface. So if that's the extent of your LiDAR processing, then the the non-module approach will certainly work for you. All of the additional line items are obviously features that enable a lot more advanced processing. Terrain surface using the DTM DSM processes that Katrina just demonstrated, the filtering options we went through, reclassification of points, automatic reclassification of points based on those geometric characteristics. Cross-sectional viewing, something we used a lot during our scenarios, that's only available with the module. Ground point detection is a huge one. Probably the most important component of the module is identifying ground points and then reclassifying those ground points. It gives your data much more utility, much more useful if you can identify which points are ground. You may find in your point cloud a lot of the points are unclassified. Without an inherent classification, there's really not much you can do with them with any level of confidence. That tool improves the quality of your data significantly. And then we get into specifics, the building tree and power line. And by the way, that list will expand. This is a work in progress. We will be adding additional extraction capability to identify other geometric features. Building trees and power lines are available in today's build. And then the extraction, the ability to actually take those reclassified points and derive vector objects from those. So as you can see, hopefully there's enough evidence, enough justification in this list to answer a resounding yes to the question, do I need the LiDAR module? We would certainly recommend anybody doing anything with LiDAR over and above the basics, at least take a look at the LiDAR module. And as we've demonstrated, fire up a demonstration or evaluation, I should say, of the application or of the module and put it to its test.
So thanks for watching. Looks like we've run out of time here. It takes a while to go through all those fancy tools in the LiDAR module.
Yeah, and if you have questions, as we mentioned at the start, I mean, obviously these recorded presentations, there's obviously limited scope for interaction, but we want to make sure you stay in touch. We know there's probably things that we maybe left a little bit loose. If you have any questions, you want clarification, you'll see some communication options on the screen. There's our email inbox. Our esteemed tech support crew are ready and willing to help you with any questions you have. geohelp@bluemarblegeo.com. The forum is also a great location, a great venue to both share information about your experiences or to find out what other people are doing, post questions, browse through some of the archives in there. If you're not registered on the forum, I strongly recommend you do that. And obviously, we've got our website there as well if you want to try Global Mapper. We will, as I said, we will provide a link to the download right in the description underneath our YouTube video. So you'll hopefully see that in the description below this presentation. So thank you very much for your help today, Katrina.
Thank you, David.
We look forward to speaking to you next month.